and welcome to the second in our webinar series, Connection Regardless of Location. This session will focus on rail and train coverage. My name is Sam Dilley and your speaker today is Ingo Floma, one of our product managers here at Axel Wireless. We've got a very interesting webinar today, and before we start, I just have a couple of housekeeping points. During the webinar, you'll be placed on mute to avoid any feedback and to ensure we finish on time today. If you have any questions for Ingo, please send them via the chat option, which you can find on the right-hand side of your screen, and we'll get through as many as we can at the end of the webinar. Okay, let's get started. Over to you, Ingo.
Hello, everyone. Welcome to today's webinar. My name is Ingo Floma. Some of you might have met me before. I'm responsible for the EMEA region for Axel Wireless, and I will walk you through the next 30 minutes. I have some history in onboard coverage. I started in '99 to work on the first project with hundreds of units, and since then it has never stopped. And actually I see a growing trend in both railway track coverage and onboard coverage. So I'm glad that so many people have dialed in. Thank you for that. We will have a question and answer round at the end of this session. I hope you ask a lot of questions and everyone can benefit from questions. So I encourage you to ask. So what we will do today, first an introduction, who is Axel Wireless, then a bit about rail and train coverage, the reasons why to do it. Then we talk about Axel Wireless solutions for both railway and train coverage. And we want to discuss a real case study, a project we have done in the UK using Axel Wireless onboard repeaters. And then we will continue with the question and answer round. The session should last around 30 minutes roughly. So let's get started. Introduction, who are we? Axel Wireless is a global company. We are based in the UK. We have facilities in other places in the world as well. We are the biggest European manufacturer for repeater and active DAS equipment and wireless coverage solutions. We consider us as the world market leader for public safety coverage systems. And we are now part of COPAM. COPAM has acquired us last year. COPAM is quite a big company. It's listed at the London Stock Exchange. COPAM is very well known in the defense and transport business. Not so much with radio solutions, but more with refueling systems, for example, with antenna solutions and special devices for this market. Axel Wireless provides solutions for cellular, for public safety, and for railway and transport applications. So that's a good range of applications that we cover, and we do that for more than 40 years. Our company consists of two companies. One is AFL in the UK, and another one is ABI in Sweden. So some of them might know one of our historical predecessors, and we are now Axel Wireless. What do? We do not offer very low-cost product. This is not our focus. Our core focus is quality and innovation, and we invest a lot into innovation, and it's funny to see that our quality level is highly demanded in low-cost markets such as China, where we are present in almost all metro systems. So it's not the low price that counts there, it's the quality that counts. So we get confirmation for our course. We are present in more than 150 countries, and this is growing since there are some emerging markets like Africa with a lot of countries and so on. Also, the number of operators we are supplying to is growing across the globe. We support 16 offices. That's not so much. Also, our number of employees, 250, looks very slim, and it is really slim. We concentrate on R&D and design and strategy. We have outsourced most of our production, and we run partner systems all over the world. That means you have a direct sales contact from our partners usually, and local support. We are proud to be listed as innovation leader by ABI Research. This is a research that was done this year around February, where Axel Wireless is ranked #1 in innovation, mostly due to our revolutionary IDDAS concept, a digital distribution concept with capacity switching ability. I'm sure you will hear more about it in the coming weeks. In total, we are ranked number 3 when it comes to volume, and we are pretty happy with this. First of all, because it's the best ranking for a European company. Second, the 2 other companies being listed higher than us do much more portfolio-wise than we do. They do passives, they do cable, they do connectors, antennas, and so on. So we are really happy with our ranking just doing active equipment. Our market share grows. We are strongly growing, especially in our home regions, where we have in many countries more than 50% market share in the cellular business. That's a total difference to the situation 4 or 5 years ago. So now we talk about reasons for rail and train coverage. What is the motivation for it? First of all, there are no coverage zones along railway corridors, which automatically leads to no coverage zones inside trains. So both is a bit related. And the other issue is to penetrate a train. It requires a bit of more signal outside the train to go through the windows. So that's why onboard repeaters can help to overcome this and increase the track length covered with signals. Trains are traveling at high speeds, and passengers, especially on high-speed trains, expect good service, good data throughput, and that's a bit of a contradiction because it's more difficult to cover a high-speed train. But we show you approaches where it's really easy and safe to sit in a high-speed train and be connected. We see expectations today that can exceed 1 gigabit per second delivered to the train. So you can imagine this requires a pretty good distribution system along the track, using every megahertz of available spectrum and MIMO, of course, to get it across. The traditional methods of using base stations, either along the track or somewhere in the rural areas, have limitations, because the coating of trains, especially when they are thermally insulated, reflect RF as they reflect sunlight. So that's all not too productive to get coverage inside a train, and that's why the industry has found solutions to get pretty good signals inside trains. Commuters want to utilize their travel time to work, but a lot of private passengers use iPads and mobile devices to check their emails or use the internet. It's a pretty wide requirement to use internet on board of trains and voice anyways. So who benefits from a train coverage system? For the traveler, obviously, it's a better use of time while traveling, quality time spent while traveling, uninterrupted connections to the outside world through voice calls, text, emails, and internet. And both of this, it's different than using planes. In planes, first of all, you have to shift your location several times. You are checking in at the airport, then you're waiting again, then you have to get up again to board the aircraft. Then during the flights, you're typically not allowed to use phones, or there is no connection anyways. The same happens after arrival. In a train, it's different. It might take longer, the actual trip time, but you're sitting at one place, you can concentrate much better. And if you have connection to the outside world, you can use your time really efficient. Additionally, systems on board of trains increase the safety for travelers because you have a way to communicate to the outside world. For the mobile operator, it's a greater customer satisfaction with permanent network availability. It's increased revenue, especially with the premium business users and with roaming customers. So if a roaming customer jumps on a train from an airport, he will stay on the network and not change, which is a great contributor to the revenues with roaming customers. For the train operator, again, it's a greater customer satisfaction. That means the utilization of trains might grow. It increased safety for passengers, but also for staff. Usually, train operators are using standard cellular signals for communication, for internal communication. We all know there is a system called GSM-R. It was originally designed for both voice and data, but it's more or less 100% used for signaling to the locomotive and not for voice, and there is no additional capacity. So railway operators have to rely on cellular signals along the tracks and inside the trains. So how do we solve these issues that we have seen? First of all, this is the simple schematic how it is done actually. We pick up signal outside the train on the roof at the highest position with the best line of sight conditions to the outside world with an omni antenna. And that's a big difference already. Just the antenna situation makes a huge difference to the standard way of sending signals to the window. A lot of it get reflected. The angle of arrival is usually not optimized, and not much goes into the train. So the rooftop antenna, first of all, it's omni and has direct line of sight to many base stations. Second, it's on a high position, so it receives more signal than you will have on seat level. And this signal, this relatively good signal, is brought to a repeater, a digital repeater. A digital repeater has the ability to filter subbands and operator-specific bands and amplify them differently, because what you realize is operator A might have a base station near the train, operator B has a base station far away from the train. So you have different requirements between the different operators, and a digital repeater is able to handle them separately and deliver a high quality at the output side. So the output of such a repeater is brought to a coverage system, preferably a leakage cable. Leakage cable has the advantage that it provides a very homogeneous signal along the whole train. The alternative is to use antennas, and we are doing that as well, but we do not recommend to do it. Sometimes we are forced to use antennas because there is simply no way to install a leakage cable because it's shielded by metallic surfaces or whatever reason it is. So antennas work as well, but obviously they don't provide this harmonic coverage as a leakage cable does. We have developed two different models of onboard repeaters. One optimized for single carriages, which is our DOBR compact. The other is optimized for multi-carriage trains, and the market is twofold, I think. We have a lot of traditional trains with individual carriage management. For them, the DOBR compact is the perfect solution because it's a bit smaller. It can have 5 bands, so that's all the European spectrum in one system, while the DOBR medium power has more power, can carry more mobile signals back to the base station, so you can combine multiple carriages to one repeater unit. And if you look on the landscape in Europe, most of the high-speed trains are multi-carriage trains. This is a real result that we have measured, a typical result in a train. The upper graph shows the outside signal. That's what the rooftop antenna receives, and you see it looks pretty wild. There is a big spread of signal power. You get very strong signals, you get very weak signals, and we all know, everyone who works in network planning understands that a signal below 100 dBm is not really a good signal, and you probably drop the call, especially when you have to go through the window before you hit the mobile phone. So after the repeater, that's the graph at the bottom, the signal looks much more defined. You can see that the main signal and mean signal level is in a pretty good range, around next 65 dBm, and that's what the mobile phone likes to see to perform very well. So you can see that the repeater has improved the signal quality a lot, plus the receive power. So these are two things that a digital onboard repeater does. Another thing that is not visible here is the speed factor. Imagine a train going at 300 kilometers per hour has a pretty fast approach speed to an antenna and to a base station. That means the repeater has to react very fast to reduce gain or increase gain, and the digital repeater has the ability to do that. Axial wireless repeaters are using patented algorithms for this, and they are really optimized for these high-speed conditions. Further measurement results are RX level. The white columns are systems without onboard repeaters. The purple colors represent systems with onboard repeaters. And you see that the RX level is much higher in a system with onboard repeaters. Now I move directly to the third column here. And here that's transmit power. And RX level and transmit power is related. So what happens when you get a good RX level? You have a much lower transmit power, and you can see that. The purple column is much smaller than the situation without repeaters, where your mobile needs a much higher transmit power to get outside. And why is that so important? First of all, it's battery lifetime. A train journey can be very long. It can be 6 hours or longer. And if you talk a lot, your battery might be empty after 3 hours. And if you have a low transmit power on your mobile phone, the battery lasts much longer. So operators love it. They get more airtime. But also the interference situation is much better. You have less interference inside the carriage. From the health side, it looks much better. So that again speaks for onboard repeaters. Then there is the number of dropped calls, which is so much lower using an onboard system. It can be 10 times better or even more using onboard repeaters. The number of dropped calls will go down a lot. Related to that is handover success. That means when the train moves from one cell to the next, the rooftop antenna sees the neighbor cell much earlier. The amplification of the repeater allows the mobile phone to adjust to the coming neighbor cell much earlier. So the chance that the handover is successful is much, much greater using onboard repeaters. But to get a good signal on board of a train, it requires a good signal along the track. The repeater cannot make anything better than is given to him by the outside conditions. So for that reason, you need a quality signal along the track, especially when it's high speed and especially when high data throughput is required. What optical distribution systems do is they allow you to create extra long cells. In this example, we show 20-kilometer track lengths, and this is absolutely possible to do. The limit is not really the fiber length or anything, it's basically the timing limitation of the system. So GSM allows for up to 20 kilometers range in one cell. So what advantages does it have to have one cell? You can imagine on a train track, you don't have a train at every antenna. The train might be at 1 or 2 antennas and 10 other antennas are in idle mode. So you can create long cells without having capacity issues, but you have a big advantage. You avoid handovers. You have no handovers on a 20-kilometer length. That means you don't lose signaling traffic. There is no risk of a dropped call due to handover, and it's a much safer and higher throughput approach. So that is a typical application that we find on many high-speed tracks and in many tunnel systems, for example, Eurotunnel. And this is a main advantage of using optical distribution. Further, we can define overlap zones much better because at a certain time you have to do a handover to the neighboring cell, and we can put the neighbor signal to a remote that also distributes the current signal. So you have a radiation of 2 cells at the same antenna, which allows much better handover. And we should be aware what a handover length is in a high-speed condition. If it's a train with 300 kilometers an hour, we talk about 700, 800, 900, 1,000 meters handover, and even more. It depends a bit on the quality and the throughput and so on. But that's quite a long distance where mobile phones are in handover mode, and we can reduce that handover zone by optimized coverage. And here is another bonus that you get with an optical distribution system. We can provide a corridor or dedicated cell along the track. Dedicated cell means the customers using the train, stay in this cell. They have no handover relation to the neighborhood, to the outside world. They stay on this railway dedicated sector until they arrive at the railway station and move out. The advantage is if there is, for example, a traffic line or a high-speed highway in parallel to the high-speed railway line, and there is a traffic jam on the highway, what happens? The cell is fully utilized usually. You might have experienced that when you try to make a call in a traffic jam. Very often you can't get through because the cell is totally out of capacity. And if a train rushes in such a cell, of course, all the calls on board of the train will drop because there is no capacity to catch these passengers. By providing a corridor for the high-speed railway line, you prevent that. There is no handover relationship between highway and railway track, and you have a much better quality. An optical distribution system consists finally of the remote units. Remote units are the elements installed on the mast or in the tunnel. The advantage of using Axel AEM40 systems is that we can combine 4 bands in one box. The form factor is really attractive if you compare that to remote radio units, and you would need plenty of those, one for each band, one for each operator. You could end up with 12 or more remote radio units, and they are replaced by one remote unit, as you see here. IP65, usually passive cooled, up to 20 kilometers distance from the master unit. Master unit is this gray rack you see there. Master unit is the interface between the base station and the optical fiber. The master unit is also the controller of the whole system. It has a SNMP interface to the outside world. It has a web server-based controller, so you can dial in anytime or sit there locally and monitor the entire system. Axel Wireless further offers a AEM monitoring solution to have the full details and to reduce the workload, but it's not required. It's very important to understand. There's no necessity to use a proprietary ONC solution when you use Axel Wireless equipment. We provide standard SNMP, which is good enough to do most of the controlling functions. So again, this kind of approach is used for both tunnels and open track railways. It can be used for MIMO as well, no problem. Then it's a double infrastructure approach. And the best for the mobile operators, the same approach can be used for in-building, for stadiums, and so on. So the spare part synergy is fantastic. This is a typical screenshot of a web server. So that's the user interface we provide on board of these units. It's easy to use. You can see a lot of measurement values to optimize your network, but it doesn't have to be complicated. You can just forward summary alarms if you like, and we do even SMS alarm forwarding. Now let's look into a real case. We are covering the East Midland train fleet in the UK, the railway line going from London to the northwest. And it consists of 27 trains. The trains are different in length. They have trains with 3 carriages, 4 carriages, and 5 carriages. And we have designed a solution for East Midland trains that allows to use the same repeater approach with different couplers with a smart coupling system. So you can use from the same base approach the system for 5 carriages, and the same system can be used for 3 carriages. So that reduces cost of operation and CapEx as well. We provide coverage inside the trains for all different cellular bands. The speed of this train is 200 kilometers an hour. This is not record speed. We have done much faster trains. But there is another complexity here. Trains going through rural areas, not dedicated high-speed trains, usually don't have dedicated track coverage systems. That means the East Midland train goes through sometimes weak coverage areas, and the repeater has a lot of work to get them amplified, filtered, and delivered to the train. That's why it's harder for a repeater system to provide good quality signals without dedicated track coverage systems. And I think in East Midland trains we are showing that it works, that you can rely on standard base stations in rural sites around the railway track, and you still get a satisfactory result. So the complexity here was further that the system was a retrofit. It was not built into the trains from the beginning, so it had to fit into the layout of the train. And that wasn't too easy because space was limited as usual, and cable runs and so on had to be found. And in this case, in this project, we contributed directly from Axel Wireless. We provided a lot of services. And furthermore, we are doing the full monitoring for this system. So we have a 24-hour NOC in our headquarters, and we are monitoring the entire train fleet of these Meridian 222 trains. That's how our unit looks like. In this case, we use the medium power version because we are providing coverage to multiple carriages, up to 5 carriages from one repeater. In this project, it was a tri-band unit because LTE was not deployed. As I mentioned before, we are doing 5-band systems as well, covering the whole European spectrum. The exterior antenna picks up the signal. It's on the rooftop. And then we have feeder cables to 2 antennas inside each carriage. So here we could not use leaky feeder. So we used antennas, and it still works. Then onboard repeaters have to be designed to withstand the physical challenges. We have to prove that we can resist the vibrations on a train, the large temperature variations. Imagine a switch on in a cold train on a winter morning. It can be below 0. And in summer, usually inside the trains, the ventilation is not always so good, so temperatures up to 50 degrees must be expected. So the benefit here is that passengers stay connected when they are traveling. Remote access through the Axel Element Manager allows to monitor the units inside the train. And it's very interesting to see in our NOC on the map of the UK these moving spots, because you can monitor the position of the equipment, which is very important. Axel Wireless repeaters have a GPS interface. It is not only important to see where they are, it's also important when they send an alarm to find out why they send an alarm. But because in an onboard scenario, it's very few cases that the repeater actually is causing the alarm. It's usually that the power is off because the train is parked somewhere, or there is no coverage because the train might be in a tunnel that has no coverage. So for that reason, localization for onboard monitoring goes hand in hand with the actual alarm monitoring to understand why there is an alarm. We support all cellular services on this train, and there are happier commuters, happier train and mobile operators. So we believe that this is a pretty good example. Thank you for listening that long. I guess we have some questions, and I hope that Sam will forward some of them to us, and I'm happy to answer them.
Thanks, Ingo, and thank you everyone for listening. Yes, we have had some great questions come in, so I'll get right on to them. First question is, how do you connect the radiating cable between the carriages, or do you provide a separate system for each carriage?
That's a very good question, and we offer both options. As I said, we have a medium power version to cover multiple carriages. Standard situation, we do it quite often. Then the other situation with individual carriage management. And it's not only what I said before that you can manage the carriages individually. This is a growing requirement even in multiple unit trains. In this high-speed trains with multiple carriages always connected together. Because of these cable runs between the carriages, some operators decide to go for low-power individual carriage coverage systems, because then they avoid the cable run between the carriages. It has another advantage. Repeater per carriage is more able to react to the path loss changes because it is a finer resolution. When you have one antenna for 5 carriages, that's already 150 meters of train length, and the end of the train might be 150 meters away from the base station, well, the beginning of the train is right under it. So we see a growing market for individually managed carriages. But if there is a reason to do multiple carriages, there are solutions to connect them. We use feeder cable, we use flexible cable. It's still RG214, which is a heavily used cable for this because it's robust. It's not the best for RF, but remember, it's quite a short run. It's maybe a 2-meter run from one carriage to the other, so the loss is not so important. Best is to use standard RF connectors, 7/16, but in some projects it collides with the operational requirements of the railway itself, and then we have used different connectors that were approved by the railways.
That's great. Thank you, Ingo. Right, the next question I've got, is a repeater required for each rail car?
Yeah, that relates to the question we just heard. So again, we have both solutions, and I see a growing market for individual solutions, and therefore we have developed this compact, and we are developing we are actually working on another step where the power is more reduced, but more important, the size is reduced and the power consumption is reduced and the cost is reduced. So all this gives advantages when you want to do single carriage applications.
Okay, great. And the next one I've got is, what is overall burst, delay, repeaters, cables, couplers, if any of?
Did I understand right? It's about delay?
Yes, that's right. So what is the overall
major
burst
delay? Yeah, I'm not sure if I got it right, but I tried to answer as best as possible. The delay, the majority of the delay is created by the filtering in the repeater itself. That costs about 6 microseconds delay. But it's a standard situation in any channel selected or band selected repeater, so that is proven since 20 years in GSM. This works, and there is no problem. But there are other delay issues, so I'm not sure in which direction this question goes. So I suggest that you send your question by email that I can answer in detail, because it could also be the total delay to the train or the differential delay approaching a base station. So please send your question by email.
Okay, great. And the last one I'll ask is, do you see a demand for MIMO in onboard applications?
Actually, we do. And that's a bit contradictory, because there are two tendencies in the market. One tendency is for highest data throughput, and the other tendency is for lowest size of the equipment and lowest power consumption. Not everything goes in one step. So we are able to offer MIMO, and the results are fantastic. So you get MIMO on a train, but it requires more space. So if you have the space, it's a fantastic approach to use MIMO, but many trains just allow 4 units, 19-inch, for example, and well, some operators, some projects think they can get 5 bands and all of them MIMO, and that doesn't work. Technology is not on that level. There are no amplifiers that can do it in that size. So it has to be a trade-off. It has to be a synergy between the two demands, but it's possible, yes.
Okay, that's great. Thank you, Ingo. Okay, we've run out of time now, so we'll follow up on any other questions via email, but if you do have any more, please email them to Ingo. His details are on the slide in front of you right now. We hope you enjoyed the webinar, and thank you for attending. Goodbye.
Thank you all. Bye-bye.